find the gravitational potential within a solid sphere. The mass of the solid sphere is capital M and its radius is capital R, and we are interested in finding the gravitational potential at a distance small r, that is any point A which is at a distance of small r from the center. So over here we shall be making use of once again what we learned in the case of shell. That is, in case of a shell, if we have a thin shell over here and if we have to find the gravitational potential over here, which is the point which is outside this, so it comes out to a minus gm upon r. We assume the whole mass to be concentrated at center and directly we say minus gm upon r, so this is gravitational potential at A. And if you have to find the at surface, so potential at surface, it comes out to once again minus gm upon the radius is capital R minus gm upon r, and the gravitational potential is going to be same whatsoever is at the surface of this shell, the same is going to be within this shell. That is, if we have a C point within this shell, so the potential of C is same as that of the surface itself. This is in regard to a very thin shell. Had it been thick, then once again, as we used earlier, the methods of integration, then we find what is the gravitational potential at the inner surface or within the cavity or at the outer surface. So over here we see that is we have to find the gravitational potential at a distance r. So over here one is gravitational potential because of this mass. Let's call this as m dash. So this is a sphere of radius r, and at the surface we can easily find the gravitational potential because of this mass at the surface. Let's say the inner sphere has a mass m dash. So because of this, at this surface the potential is gravitational potential is going to be minus gm dash upon r. The contribution of this is done over here. Now what we have to do is we have to find the what is the gravitational potential because the rest of the mass over here, that is, if we say this is the marked shell, now because of this region we have to find what is the potential over here at the point A. So what we do is once again we consider, now this part is over, now let's remove this. Now its contribution has already been taken care of. Now we are bothered about what is the contribution of this mass, remaining mass, towards the potential, gravitational potential at the point A. So what we do is at a distance x, we take a very thin shell of thickness dx. Thickness dx we are done, we have taken, right? And we are taking this outer shell mass as m double dash. So if we have to find what is the gravitational potential because of this thin shell at this point A, as we did earlier in the case of a shell of some thickness. So now let's talk about this contribution. This shell has surface area 4 pi x square, radius is x, thickness is we have taken as dx only, thickness is dx. So surface area 4 pi x square into dx, area into thickness, that is volume. Volume to density is mass, so it is differential element of mass of this shell we get. The gravitational potential because of this within this is obviously we say it is minus g dm upon, so whatsoever is its radius, minus g dm upon x. So this is differential element of potential at point A because of this thin shell of radius x and thickness dx. And if we are to find the total contribution towards potential by this mass, this outer shell, so we integrate it. From where to where? We integrate the first shell is at a distance small r and outer shell is at a distance capital R, outermost shell is at a distance capital R. So we integrate it. So now over here the point to note is that is density is same. Whether we take the inner sphere or we take the outer sphere, the density over here is going to be m upon 4 by 3 pi r cube. So the gravitational potential at point A because of this outer thick shell, it comes out to be minus 3 gm upon 2 capital R cube r square minus r square. So this is the contribution of this outer shell. And what is the contribution towards potential at the point A? Yes, we know it is minus gm dash by r, where m dash is the mass of this sphere of radius small r, and this comes out to be once again mass is equal to volume into density. What is the volume of this inner solid sphere is 4 by 3 pi small r cube into density upon r. What is the density? Density is total mass by total volume. It is a solid sphere, so we can do it total mass by total volume. And when we solve it like this comes out to minus gm r square by capital R cube. So if we are to find the total potential at the point A, which is at a distance small r from this center, it is going to be this potential, that is potential because of this, plus potential because of this outer shell. We add the two. This is VA, we have got it from here, and Vm dash at A, we have got it like this, minus Gm dash y upon minus Gm dash upon R. We can put this value, so we can add 1 and we can add these two, and we can get the total potential within the solid sphere at a distance small r from its center. So once we find the gravitational potential at point A because of this inner solid sphere of mass m dash and the outer shell marked in black of remaining mass, that is m minus m dash, we find the potential because of this outer shell at the point A. Rest is very simple. Gravitational potential being a scalar quantity, we can add the two potentials because of this solid sphere and because of outer shell at the point A, and this comes out to be, that is potential at A, that is total potential at A is equal to potential at A because of m dash, that is inner solid sphere, plus potential at A because of this outer shell. When we add these two, they are simple calculations. It comes out a minus gm2 r cube 3r square minus small r square. And if we are to find what is the potential if the point A is at the surface, so it means this r becomes equal to capital R only. So in this we put r, small r as capital R. So when you put small r as capital R, it obviously comes minus gm upon r. That is what was expected. And if we are to find what is the potential, gravitational potential at the center of this solid sphere, then we put small r is equal to 0. And we put small r is equal to 0, this comes out to be minus 3 by 2 gm upon r. That is V at center comes out to be 3 by 2 of the gravitational potential at the surface.